Okay, so this is the second, or sorry, this is the third already, the third video for investigation two. So we're gonna practice computing some limits using one of the three methods of our choice, and then we're gonna apply this to what we just talked about in terms of vertical and horizontal asymptotes. So, you should use whatever method you want to use as long as you justify your work um, in a logical way, that's fine. I'm going to, at least for the first four, I see that these are rational functions, so I'm going to use that trick that I told you about to divide the top and bottom by the highest power of x in the denominator. So, like for the first one, the highest power of x in the denominator is x to the first. So I'm going to divide the top and bottom entirely by 1 over x. So make sure that you distribute fully. And by the way, I'm doing this because if I just try to directly plug infinity on top and on bottom, they both go to infinity, and infinity over infinity is an indeterminate form. So that's why I need to simplify it. So if I do that, I'll have the limit as x approaches infinity of 1 plus 4 over x all over 1 minus 6 over x. And as x approaches infinity, 4 over x approaches 0. This is like 4 over 100, 4 over 1,000, 4 over a million. So you guys can remember that a number over something that's getting really big gets really small, right? So these both go to 0. And now we take the limit, and so this will equal 1 plus 0 over 1 minus 0, which is 1 over 1, which is 1. Okay, so for the second one, the highest power on the bottom is x squared. So I'm going to divide top and bottom by x squared. And so this is going to be equal to the limit as x approaches infinity of 3 plus 4 over x squared all over 1 minus 6 over x squared. And again, as x approaches to infinity, the two circled terms both approach 0. And so this limit is equal to 3 over 1, which is 3. Okay, for part 3, I have the highest power on the denominator is x squared. So again, I divide top and bottom by x squared. And so this will be the limit as x approaches infinity of 1 over x plus 4 over x squared all over 1 minus 6 over x squared. And so all of the three circled terms will go to 0 as x gets arbitrarily large. And so totally this limit will equal to 0 over 1. 0 over 1 is not an indeterminate form. That's equal to the number 0. So this limit equals 0. Looking at number 4, the highest power of x on the denominator is x cubed. And so I'm going to divide the top and the bottom by x cubed. And so then this is equal to the limit as x approaches infinity of 4 plus 4 over x minus 3 over x squared all over 5 over x minus 6. And again, all three of these terms that I just circled will approach 0 as x approaches infinity. And the whole limit is equal to 4 over negative 6, which is the same, if you want to simplify it a little bit, as minus 2 over 3. Okay, so that's like a review kind of how to do the rational functions algebraically. Now, 5 is a little different because I have sine on top, so it's not truly an algebraic function. So we can review the other ways how to do this. So basically, I'm going to use my TI-84 calculator, and I'm going to go to where it says y equals on the top left gray button, and I'm going to enter in this equation, parenthesis 3e to the x plus sine x, parenthesis, divided by parenthesis 2e to the x, parenthesis. It's important to tell the calculator that this entire thing is the numerator and this entire thing is the denominator. Okay, then I'm going to graph it, and I'm going to want to choose the appropriate zoom window. So since x is going to infinity, I think I chose the window to go from like x equals negative 40 to maybe 200 or something like that. So when I got the graph off on the side here, it looks kind of crazy over here, and then I can see that it's leveling off like this. And if I really want to know what's going on, then what I do on my calculator, I click the trace button. And so like for instance, it's telling me that when x equals 255, y equals 1.5. So based on this, I suspect that the limit is equal to 1.5 by the graph. Which kind of makes sense because we know that e to the x is the dominant term on top and bottom, so it should go to 3 halves when they cancel out. But I just wanted to show you like a different way how to do it. And also on your TI, if you have a TI-84 calculator or any other graphing calculator, you can push second table. It's the little blue table above the graph on the upper right-hand side. And you can choose whatever like x values you want. So let's choose like a couple. So I put in like 1, 100, 199. So when I put in 1, I got 1.6548. And then for 100, I get 1.5. And for 199, I get 1.5. So again, based on this, I'm thinking that the answer that I got of 1.5 is correct. So it's like by the graph or by the table, we can say that the answer is 1.5. So since these other methods are a little bit less precise, it's not going to hurt you to do it 2 ways because it's almost like easy to do them both on the calculator if you do one. Okay, so for part 6, we have the limit as x approaches infinity of 3x squared times e to the negative 2x. So I know that x squared will approach infinity, and e to the negative 2x, that's like e to the negative infinity. So what I think I'd like to do is rewrite this in a way that makes it easier for me to interpret it. So I know that this is the same as 3x squared over e to the 2x because the negative exponent causes the reciprocal to happen. And then if I think about this now, basically what's happening is more clear because, because I have a domination now. So I have an exponential function in the denominator, and I have a polynomial function in the numerator, and so I know that the bottom is much, much bigger than the top. So this will go to 0 by domination because e to the 2x is much, much bigger than 3x squared as x approaches infinity, okay? So again, you can use whatever method you want. I'm just showing you like one way how to do it. And in the last part, the only difference that we have is that now x is approaching to negative infinity instead of to positive infinity. But that actually kind of makes things a little bit easier, in fact, because if you think about 3x squared, so I know that x squared for sure, this is just x squared, or we can even think of this as being 3x squared, just a rough sketch. As x approaches negative infinity, this y approaches infinity, so 3x squared is going to infinity. And if I take e to the negative infinity, that's e to the positive infinity. So this is a huge number. And in fact, a huge number times a huge number will always be a huge number. So this limit is just equal to infinity. Sometimes you can check and see what happens when you plug it in, and it's not really an indeterminate form like infinity over infinity where you have to rewrite it. It's one where we directly know what's happening. Okay, and then the last problem is just to identify horizontal and vertical asymptotes from any of these types of limit statements. And so just to review, so for a horizontal asymptote, we want an example where x is approaching plus or minus infinity and y is approaching a number. And I can see that that's what's happening actually on the first like four problems. So if you think about number one, right, it first of all, it just matches with the definition that's given algebraically. And also, if you're more of a graphical person, here we have x is approaching infinity and y is approaching 1. So I know that this is going to be a horizontal asymptote type situation. So one function above that's having a horizontal asymptote is the function y equals x plus 4 over x minus 6. It has the horizontal asymptote at, excuse me, let me look at the problem statement again. So it has the horizontal asymptote at y equals 1 because the limit is approaching 1. Okay? And for part C, we're asked if any of these have a vertical asymptote, but a vertical asymptote, we would need x to be approaching a number and y to be approaching infinity. But if we look at every single problem statement, it's always the case that x is approaching infinity or negative infinity. So we don't really know from that which ones of these have vertical asymptotes by the computations we did. But for example, the first one, it does also have a vertical asymptote because, and I know this because the denominator will be undefined when x equals 6. So I can check what happens. What's the limit as x approaches 6? Sorry, let me put the zoom in a little bit so that it's going to be easier for you to see my writing. So what's the limit as x approaches 6? Say from the right of x plus 4 over x minus 6. So if you think about this, if I take numbers that are close to 6, but a little bigger than 6, such as if I plug in 6.1, then I'm going to get a very large number that's also positive. And so because this limit is equal to infinity, I could create a table to justify this more, but this is just asking us to name one. So this means that the function y equals x plus 4 over x minus 6, it has a vertical asymptote at x equals 6. Okay, and in fact, if you graph the function, then what it really looks like is, so this is at x equals 6 and y equals 1. And what the graph looks like is something like this, okay? So that's like the whole picture of it. And in terms of how to obtain the entire graph, we're going to go into that further in some of our applications of derivatives later on in the semester. Okay, so the last problem is optional, so I'm not going to include it on the video. So that's the end of this investigation.